Good morning everyone. Welcome to the second lecture of our week number 2 where we are talking about the thermodynamic property relations. So, how was the previous lecture? I hope it has gone down well to you where we have tried to develop the Maxwell's relations using the TDS equations, and from there we have got some generalized expressions for the changes in internal energy and enthalpy of any thermodynamic system. Now, if the lectures are clear to you, that is excellent. If that is not, I would request you to go back to the previous lecture and just listen the lecture once again. If was required, go through the books. There are several standard textbooks available on thermodynamics. I have told earlier also I am particularly following the book of Sengel and Bowles. However, you can also refer to the book of Sontag, which is a very standard book, or any other traditional book on thermodynamics, and all these topics are always covered there. So, please proceed with this lecture only when you are clear with the development of the Maxwell's equations. Now, just to quickly summarize what we have done in the previous lecture, we have seen that there are four primary thermodynamic potentials, namely the internal energy, enthalpy, Helmholtz free energy and Gibbs free energy, each of them having their own implications in different kind of thermodynamic systems. Now, once we express the rate of change, or I should say the change in each of those thermodynamic potentials in terms of entropy and combination of other thermodynamic parameters, then correspondingly we can get four Maxwell's relations. The Maxwell's relations are basically partial differential equations which relate the changes in temperature, pressure, specific volume and entropy. Remember the first three properties, temperature, pressure and specific volume, they are directly measurable properties, whereas entropy can't be measured directly, and therefore Maxwell's equation serves the basis of calculation of entropy as a function of the other three. We have also discussed about the Maxwell square, which is one of the easier way of remembering all the four TDS equations and the four Maxwell's relations. I hope the use of the Maxwell square you have understood. Please try to develop the Maxwell's equations and all the four TDS relations in terms of the TDS, or in terms of the Maxwell square, so that you are in a better position to make use of that. And then we have developed generalized expressions for the changes in internal energy and enthalpy. Quite a bit of mathematics was involved there. I hope you have tried to do that on your own, try to develop the final expressions for du and dh. If you have not done that, then please pause this lecture here, just take your pen and paper and develop those relations. If you have any doubt, you can refer to the previous video and also the textbooks, but please proceed with this video only when you are able to develop the relations for du and dh on your own, because not only in this course, in several other scenarios you have to make use of those relations, and it is very rare that you are asked to develop the equations for du or dh. So, you may be thinking that what is the need of that, but there are several situations where you have to calculate some other parameters, or maybe the changes in enthalpy or changes in internal energy of a thermodynamic system, where you have to make use of those relations, and therefore you need to remember those relations. Now, those are quite complicated relations, even I am also not in a position to remember that, but that is much easier to develop the relations by taking 1 or 2 minutes before solving any particular problem, and therefore it is important that you know how to develop these relations. So, today we shall be developing the similar relation for changes in entropy to start with, and then we shall be seeing examples of applying those relations. So, the first term, or our first target, is to develop a generalized relation for changes in entropy. Now, while we had only two equations, or sorry, a single equation for changes in internal energy and a single equation in changes in enthalpy, changes in entropy can be expressed in two possible ways, and which one to use, that depends upon the available information. Once I develop the equations, we will be able to see how we can use each of them in separate situations. Now, in the first case, we are assuming entropy to be a function of temperature and specific volume. So, what we can write for ds, your ds can be written as, therefore, dou s dou t at constant v dt plus dou s dou v at constant t dv. Here now there are two relations that we have to make use of to substitute each of these partial differentials. One of the relation that we have developed while developing the expression for du. Remember, there I told you to keep this quantity separate. There also we encountered this quantity dou s dou t at constant v. What was this expression for this? I asked you to remember this one, to keep it separately, because we have to make use of that in future. So, it was in the form Cv upon T, whereas so this one can be replaced as Cv upon T dt, plus, to replace this we have to make use of one of the Maxwell's relation. So, what is that? This is the one that we are going to make use of. So, correspondingly we can say this to be equal to dou p dou t at constant v dv, and therefore, if a system is undergoing a change of state from state 1 to state 2, then we can easily represent the corresponding changes in specific entropy as integral Cv upon T dt, integrating from temperature T1 to T2, where T1 is the initial temperature, T2 is the final state temperature, plus integral V1 to V2, where V1 is the initial specific volume, V2 is the final specific volume of this differentials dou p dou t v dv. So, what are the informations we need to calculate the change in specific entropy following this way? We of course need to know the PVT relationship again, because that will be helping us to calculate this particular differential dou p dou t at v, and also we need to have information about Cv. So, this is one of the expressions for changes in entropy. The other one we can develop by assuming S to be a function of temperature and pressure. So, following the similar procedure, we can write ds is equal to dou s dou t at constant p into dt plus dou s dou p at constant t dp. Now, how to replace the first differentials? I hope now you have got the idea. Dou s dou t at constant p, what is this? This one, while developing the expression for dH, we encountered this term. It was Cp by T. So, accordingly we can write, or I can write it as Cp by T dt, and dou s dou p at constant T. How can we replace this one? Using any Gibbs equation or using any Maxwell's relation. Like in the previous one, we used this particular Maxwell relation. What we have to make use of? Dou s dou p at constant T. I hope you are able to use the Maxwell square now, and from there we can develop. So, this is the corresponding equation. This will become dou v dou t at p dp. Please try to use the Maxwell square instead of directly taking the Maxwell's relation to substitute these partial differentials. Now, for a change of state from 1 to 2, we can write S2 minus S1 is equal to integral T1 to T2 Cp by T dt minus integral P1 to P2 dou v dou t at P dp. So, this is the second relation. So, in both the cases, or in the second case particularly, what are the information that we need to know? Again, we need to know the PVT relationship to evaluate that partial differential, and also we need to know Cp as a function of temperature. So, in a given situation, which one we should select? As I have mentioned, that depends upon the available information. Of course, you need to make use of the PVT relationship in both the cases, but what is separate between the two? The first expression makes use of Cv, whereas second one makes use of Cp, and therefore, if we have information available in terms of Cp as a function of temperature, which one you should go for? Cp as a function of temperature, then we should go for this one, whereas if we have Cv as a function of temperature, we should go for this one. Or let us take another scenario where we have both Cp and Cv available with us. We shall shortly be deriving the expression for Cp minus Cv, or relationship between Cp and Cv. So, generally if we know the expression for one of them, the other one is also directly available. Then if we have information available about both Cp and Cv, then which one you should go for? That depends upon what kind of process we are dealing with. If we are dealing with a constant pressure process, suppose, then what we should do? Constant pressure process means dP equal to 0. Then for a constant pressure process, this term will automatically go to 0, and then your relation will involve only a simple term, that is, for a constant pressure process you will be having S2 minus S1 is equal to integral T1 to T2 Cp by T dt, which is a very simple relationship, and we should go for this. Similarly, if we are going for a constant volume process, then we should what we should do? Constant volume process means dV equal to 0. So, this term will go to 0 for a constant volume process, and therefore, there it will be much easier to evaluate the change in entropy as integral T1 to T2 Cv by T dt, because in the second term or in the second expression we have to evaluate both the ones for a constant volume process. However, it will reduce to only a single integration following the first approach. Of course, if your process is neither constant volume neither constant pressure, then both are equivalent, we can choose any one of them depending on our convenience or depending upon other scenario. So, this is the generalized expression for changes in entropy. So, we have now got expressions for changes in internal energy, changes in enthalpy and changes in entropy, or specific for all of these quantities, specific internal energy, specific enthalpy and specific entropy. Let us try to make use of those expressions for a known PVT relationship. So, the first expression, one handicap that we have here actually is we do not know too many PVT relationship, because that is something that we are going to cover in the next week, where I shall be talking about the properties of pure substances. But one PVT relationship that you definitely know is the ideal gas equation of state, which is PV equal to RT. Let us try to make use of this expression to evaluate the expressions for changes in specific internal energy, specific enthalpy and specific entropy for ideal gases. So, this is ideal gas equation of state. EOS generally is an acronym that is often used for equation of state, which is the PVT relationship for an ideal gas. Here R is the gas constant, so that is a constant, but PVT all of them can be variable. Then first is changes in internal energy. This is the expression that we have developed in the last lecture. So, to use this expression we have to evaluate this differential first. Then go back to the ideal gas equation of state. We have PV equal to RT, or P is equal to RT upon V. Therefore, dou P dou T at constant V, that is the one that we are trying to evaluate. So, what it will be? Here V is constant, R is constant. So, differentiating with respect to temperature will reduce to R upon V. So, now what we have here? We have Cv dt plus integration RT upon V minus P dV. Now, what is RT upon V? That is P only. So, it is Cv dt plus P minus P dV, where we are making use of this particular thing, that is Cv dt, and therefore, the changes in internal energy or specific internal energy during a particular process will be nothing but integral Cv dt integrated over T1 to T2. And in a special case, if Cv is constant, or if we can use some average value of Cv over this given temperature range, then this one will become the average Cv into T2 minus T1. It can be shown that the specific heat generally is a function of, at least for ideal gases, is a function of only temperature, and therefore, we can see here that the specific internal energy is also a sole function of temperature. This is something that we have actually already used in the previous one, du equal to Cv dt for an ideal gas, but may not be true for a real gas where the equation of state is something else. Now, changes in enthalpy. I have to make better use of the space actually. So, this is equal to Cv dt for completeness. For changes in enthalpy, what we have? Here we have to evaluate this particular differential dou v dou t at p. So, P v equal to R t. Now, we separate V out from this to have R t upon P, which gives dou v dou t at P to be equal to, and P and R both constant. So, it becomes R upon P. So, putting in this expression, it is C p dt plus V minus R t upon P. So, similarly, R t upon P is equal to V, that is it becomes only C p dt. So, we can clearly see that here enthalpy is also, for an ideal gas, enthalpy is a sole function of temperature. What about changes in entropy? Here we can calculate changes in entropy following two of the approaches. These are the two expressions which we have just derived in the previous slide. So, which one we should use now? We can use, let us try both of them, because here we are not restricting ourselves to any constant volume or constant pressure process. If we are trying to follow the first approach, then we need to evaluate this particular differential which we have already done. So, putting it there, we have C v upon t dt plus dou p dou t at V, that was R by V dV. Remember, this was the expression that we have actually developed as a part of first module to calculate the changes in entropy. Therefore, following this, S2 minus S1 will become integral T1 to T2 Cv upon T dt plus R into integral V1 to V2, like this, or we can write this as, if Cv is a constant, or we can take an average Cv, this becomes Cv bar into ln T2 upon T1 plus R ln V2 upon V1. Similarly, if we use the second expression, then we have to evaluate this differential. So, this becomes Cp upon T dt minus dou v dou t at P, what it was, this is the expression. So, this becomes R by P dP. Accordingly, we have S2 minus S1 is equal to integral T1 to T2 Cp upon T dt minus R into integral P1 to P2 dP upon P, and therefore, if we can use an average Cp, then it will become Cp bar into ln T2 by T1 minus R ln P2 by P1. These are the expressions that we actually have developed in the previous module itself for an ideal gas using the TdS relationships directly. Now, this is another way of proving the same relationship, but remember the expressions that we have got here, they are applicable only for ideal gases, and generally we are assuming a constant specific heat, constant values of Cp and Cv, or some average value of Cp and Cv applicable for this. Similarly, if we know the PVT relationship, we can do it for any other kind of substances as well. Let us try another example. Here we are having another PVT relationship of this form, P plus A upon V square into V minus B is equal to RT. This is the very famous van der Waals equation of state. The development of this one will be part of the next module. Here we are just taking it for granted, and it is also given for this particular problem, Cv is a function of temperature, is a linear function of temperature given as C1 plus C2 into T. So, we have to calculate the expressions or evaluate the expressions for changes in internal energy and changes in entropy, or specific internal energy and specific entropy, using this equation of state and this particular expression for Cv as a function of temperature. So, this is the expression for du that we had. Let us try to develop the expressions for du for this particular scenario. So, use the equation of state first. We have P plus A upon V square into V minus B is equal to R T. By the way, here R, A and B all are constants. So, we can write P to be equal to R T upon V minus B minus A upon V square. So, what is your dou P dou T at constant V, the differentials? dou P dou T at constant V. So, now also as we are differentiating with respect to temperature, V also becomes a constant. So, it becomes R by V minus V, all constant, and the second term becomes 0 because V is a constant. So, if we put it here, we have Cv dt plus, here it is RT by V minus V minus P dV. To evaluate the term inside the square bracket, now let us look back into the expression for the equation of state, or maybe here. So, from here if we rearrange the term, we can also write RT upon V minus V minus P is equal to A upon V square. So, we can reduce this term as A upon V square dV. Therefore, for a change of state from 1 to 2, changes in specific internal energy U2 minus U1 will be equal to integral T1 to T2 Cv dt plus integral V1 to V2 A upon V square dV. Now, if we put the expression for Cv here, then we have integral T1 to T2 into C1 plus C2T dt plus A into integral dV upon V square to get from V1 to V2. So, what we are having here, we have C1 into T2 minus T1 plus C2 T square by 2. So, therefore, C2 by 2 into T2 square minus T1 square, and here we have V2 to the power minus 2. So, we are differentiating V2 to the power minus 2. So, it will become A into V2 to minus A into V2 to the power minus 1, that is minus A into 1 by V2 minus 1 by V1. So, this is the final expression for the changes in internal energy, specific internal energy that we are going to get in this particular scenario. Similarly, if we want to calculate the changes in specific entropy, this is the expression for specific entropy. So, there also you have to make use of this dou P dou T at constant V. So, what we have, we are putting it here. So, we have Cv upon T dt plus dou P dou T at constant V, the expression that we have developed earlier, R by V minus B dV. That is, putting the expression for Cv now, we have C1 by T dt plus C2 dt plus R by V minus B dV. Therefore, S2 minus S1 will be equal to integral T1 to T2 for the first term, which is C1 can be taken outside, it is dt upon T, plus again C2 can be taken outside, integral T1 to T2 just dt, plus taking R outside, it is dV upon V minus B from V1 to V2. And now performing the integration and putting the limit. So, we are going to have C1 into ln T2 upon T1 plus C2 into T2 minus T1 plus R into ln V2 minus B by V1 minus B. So, here again we are able to calculate from the knowledge of the PVT relationship and Cv as a function of temperature, we are able to calculate the expressions for changes in internal energy and changes in entropy. If we want to calculate the changes in enthalpy, we need to know the expressions of Cp or relationship of Cp with temperature. If we can assume Cp to be a constant, or if somehow you can evaluate relationship between Cp and Cv, then we shall also be able to evaluate the changes in enthalpy. But truly speaking, in a given scenario, we hardly have to go for changes in internal energy and changes in enthalpy both, because even without any knowledge of Cp, you can calculate the changes in enthalpy in this particular case. How can you do that? I am repeating my question. Here now we have already developed one relation for changes in specific internal energy, that is U2 minus U1, and a expression for changes in specific entropy S2 minus S1. Now, I am trying to say that we do not need to do any further differentiation, or we do not need to have any information about Cp, but still we can calculate H2 minus H1. How can I do that? Just try to remember the relationship between U and H. What is H2? H2 is U2 plus P2 V2. Similarly, H1 is U1 plus P1 V1. So, we can write this as U2 minus U1 plus P2 V2 minus P1 V1. U2 minus U1 already you have evaluated right here, and now you know the PVT relationship, you know state 1 and state 2. So, both P2 V2 and P1 V1, these two products are known to you. So, you can easily calculate this H2 minus H1. Therefore, in a given problem we generally never have to calculate both the changes in specific enthalpy and specific internal energy. One alone is sufficient, because from one we can get the knowledge about the other one, and therefore, we hardly need to have information both about Cp and Cv. Knowledge about one is sufficient. Like for ideal gases, we have developed the relation. We generally know that Cp minus Cv is equal to R, but that is true only for ideal gases. But for real gases, for non-ideal gases, this is not true. So, there is some generalized relationship that is available between Cp and Cv, and that is the next one that we are looking to perform. So, changes in specific heat is very important to know, because specific heat gives you an idea about the amount of heat required to cause 1 degree change in temperature for unit mass of a substance, and therefore, in any heat transfer application or sensible heat transfer application, specific heat or knowledge about specific heat is very important. Now, specific heat for ideal gases, it is more or less a constant, but generally it is a strong function of temperature. Even for ideal gases also, at high temperature specific heat can vary a lot with temperature, and for non-ideal gases even pressure also can have some role on the magnitude of specific heats, and therefore, along with enthalpy, entropy and internal energy, it is also important to know how specific heat is varying with temperature and pressure, and that is our next job. So, to start with, we shall be making use of the relationship that we have already developed earlier for the changes in entropy. We had two relations. One was ds to be equal to, okay, instead of trying to remember this, let us develop them again from scratch. So, we are assuming entropy to be a function of T and V, from where we can write ds is equal to dou s dou T at constant V dt plus dou s dou V at constant T dV. Similarly, if we assume entropy to be a function of temperature and pressure, then we got ds is equal to dou s dou T at constant pressure dt plus dou s dou P at constant temperature dP. We are not going to put any expression for Cp or Cv, or at least we are not going to okay. Let me correct myself, let us use the Maxwell's relations now to get the final expressions for ds that we had. That will actually help our analysis or make it much shorter. So, dou s dou T at V, we know that that is Cv by T dt, and this one using the Maxwell's relation, it was dou P dou T at constant V dV. Similarly, for the second one, we know we can write this one as Cp upon T dt minus this is dou V dou T at P dP. So, these are the two relations for changes in entropy we have developed earlier and we also used in the previous slides. Now, we know that entropy is a property. Similarly, temperature and specific volume is also a property. Here we are talking about the first one. Now, temperature and specific volume both are properties. So, if entropy is a property, then we can use the definition of property in terms of differentials, and therefore, we can write that dou dou V of Cv by T with temperature constant should be equal to dou T of dou P dou T with volume constant. Now, temperature being constant, we can take it out. So, we can write dou Cv dou V with constant temperature should be equal to T into dou 2 P dou T2 at constant V. So, this is an expression for changes in specific volume at constant volume, that is Cv, with volume itself at constant temperature. Similarly, if we use the second definition now, this one, again knowing that temperature and pressure are properties. So, for entropy to be a property, it should satisfy this condition, that is dou P of Cp upon T at constant temperature should be equal to dou T of minus dou V dou T at P. Temperature being constant, we can write this as dou Cp dou P at constant T is equal to minus T of dou 2 V dou T2 at constant pressure. So, this way we can express Cv as a function of volume or Cp as a function of pressure, and using this expression, integrating them along an isotherm for between two given state points, we can easily calculate expressions for Cp and Cv. Say for example, if we take up the second expression and integrate this from one state, from a given state point 1 to another state point 2, then we can integrate this for say del Cp along a constant temperature should be equal to minus T dou 2 V dou T2 P dP, and if we put the integration limits say from absolute 0 pressure to a certain pressure P, then Cp naught, which generally calls the absolute pressure, absolute 0 specific heat or ideal gas specific heat to certain value of Cp, then we have Cp corresponding to this particular temperature and pressure that we are talking about should be equal to Cp naught corresponding to the temperature minus T into this particular integral dou 2 V dou T2 P dP. So, this is one expression which represents the Cp as a function of temperature and pressure. Cp naught, the ideal gas specific heat or absolute 0 pressure specific heat, is a function of temperature alone, because we are talking about the absolute 0 pressure, no effect of pressure on the magnitude of this, but for different temperature the Cp naught can have different values even for ideal gases also. And the second integral can be evaluated only if we know the PVT relationship, because then we can express these differentials and then we can perform this. And a similar expression can also be obtained for Cv using this particular expression. But generally the expression, separate expression for Cp and Cv both are not required, like we have seen for ideal gases Cp and Cv are separated by the gas constant only. Similar relationship exists for even for real gases as well, and let us try to evaluate that relation. So, what we are going to do now, look at the two expressions for ds. From the two expressions for ds, let us separate, equate both of them. So, from the first expression we have Cv upon T dt plus dou P dou T at constant V dV, and from the second one we have Cp upon T dt minus dou V dou T at constant P dP. Both of them giving the expressions for changes in specific entropy, and therefore they can be equated to each other. And let us now separate out dt from this. So, to do this we are writing Cp minus Cv upon T dt, keeping dt on one side. So, what we are left with is dou P dou T at V dV plus dou v dou t at p dp, or dt is equal to t by Cp minus Cv into dou p dou t at v dv plus t by Cp minus Cv dp. We are doing quite long expressions. Is it getting boring? If you feel bored, you can pause the video, just go back, take a break and come back after 5 minutes, but still I am doing each of the steps in detail so that you are able to understand exactly what I am trying to do. I repeat, here I have just equated the two expressions for ds, and then from there we have separated out this dt quantity. Now, as per the PVT relationship, we can always write that temperature is a function of V and P. So, from there we can also write dt is equal to dou T dou V at constant pressure dV plus dou T dou P at constant volume dP. This is the simple relationship what changes in temperature. Now, we have one expression for dt here and another expression for dt here. Let us call this is equation number 1, these are equation number 2. And on the right hand side of both the equations we have dV and dP. So, we can equate the coefficients for them, we can take any one of them. Let us pick up the coefficients for dV. We could have done with dP also, that should lead to the same result, but here we are picking up the coefficients for dV. So, we have T upon Cp minus Cv into dou P dou T at constant V to be equal to dou T dou V at P, or just taking Cp minus Cv out. So, what we have here is T into this dou P dou T at constant V into the other one, this particular differential it is now becoming the inverse as we are taking the other side. So, it becomes dou V dou T at P. So, this is the expression for Cp minus Cv we are getting, and it is a quite simple expression. Again, if we know the PVT relationship, we can evaluate both the differentials. It involves both the two differentials, this one which gives the change in pressure with temperature along a constant volume line, and this represents the change in specific volume with temperature along a constant pressure line, and also we have absolute temperature here. From where we can calculate the Cp minus Cv, but instead of directly evaluating these two differentials, there are easier ways of expressing the same. To do that, let us write this once more. We have Cp minus Cv to be equal to T into the one we have just written, dou P dou T at constant V into dou V dou T at constant P. Here we are going to make use of something known as the cyclic rule of partial differentials. If we are given with three partial differentials, say P, T and V, then the cyclic rule can be represented as dou P dou T at V into dou T dou V at P into dou V dou P at T equal to what this one will be. This is a cyclic rule. Look, we are considering all the three partial differentials possible among these three variable, dou P dou T at V into dou T dou V at P into dou V dou P at T. This will be equal to, it is a very standard rule in of partial differentials, which is equal to -1. Now, look at the present expression that we have. Here we have dou P dou T at V and dou V dou T at P. From there, let us separate out the first one, that is dou P dou T at V we are separating out from this. So, what this one will be equal to minus of dou P dou V at T into dou V dou T at P. So, we are putting it back here. So, we are having a minus sign coming in, then temperature, then we have dou p dou v at t, and that dou v dou t at p is becoming squared. Now, what are these two partial differentials representing? One is dou p dou v at t, another is dou v dou t at p. First, let me write dou v dou t at p. What this one is representing? This one is giving you the change in specific volume with temperature with pressure remaining constant, and therefore, this quantity or just slightly modified version of this quantity where we divide this by specific volume, then now what we have is the change in specific volume per unit volume with temperature with pressure constant or along an isobar. This quantity is called the, what is this? Can you guess? This one you have heard in school level physics itself, change in volume with temperature per unit volume. So, this is called the somewhat similar to the thermal expansion coefficient. In thermodynamics we commonly call it volume expansivity, call it volume expansivity. This is just the thermal expansion of volume of the gas or whatever medium that we are dealing with per unit volume, and is commonly represented by the symbol beta. And what is the other quantity? We take the inverse of that, dou v dou p at temperature, constant temperature, and 1 by v. Now, what this particular quantity is giving? It is giving you the effect of pressure on specific volume per unit volume along an isotherm at constant temperature. So, if temperature is maintained constant, this quantity is going to give you how volume is going to change with change in pressure, and this particular quantity in thermodynamics we define as isothermal, as temperature is constant, isothermal compressibility, commonly represented by alpha. Actually, to make it positive, we always know for any substance as the pressure increases its volume decreases. So, V and T goes in the opposite direction, and therefore, this differential is a negative one. To make it positive, we generally put a minus sign in front of this. So, alpha is equal to minus 1 upon V dou V dou P at T, whereas beta is equal to 1 by V dou V dou T at P. So, take this back to our expression for Cp minus Cv. So, Cp minus Cv be equal to minus T, then this dou P dou V at T, what is this? Look at the expression for alpha that we have. So, this one can be represented as minus alpha into V. Similarly, we have dou V dou T at P a whole square. So, this one can be written as, oh sorry, I have made one mistake here. Here we have dou P dou V at T. So, to get this expression for alpha into picture, we should write this as 1 upon minus alpha into V. Similarly, the dou V dou T at P whole square. So, that will be coming from beta, that is beta into V whole square. So, simplify this, both the minus together makes it positive. So, we have then T by alpha into V into beta square V square, that is equal to V T beta square upon alpha, or if we write formally, then Cp minus Cv is equal to V T beta square upon alpha. This particular relation is known as Mayer relation, a very important relationship in thermodynamics, because it allows us to relate the two specific heat at constant volume and specific heat at constant pressure in terms of 4 properties: specific volume, temperature, and these two newly defined properties, volume expansivity and isothermal compressibility, beta and alpha respectively. There are Of course, to calculate the difference between Cp and Cv for any particular gas, we need to know the PVT relationship, because using PVT relationship we can always calculate the expressions for this beta and alpha, and then putting that for at a particular state point we can calculate the difference between Cp and Cv. But there are several direct consequences that we can obtain from this relation. What are those? Look at the first expression. Look at the expression for beta. The volume expansivity, or okay, before that let us look at the expression for alpha. Alpha is minus 1 upon V dou V dou P at T. Is it positive or negative? Can we say? We know that for any substance, as the pressure increases the volume will decrease, or vice versa, that is volume and pressure goes in opposite direction, and therefore dou V dou P at T is always negative. Now, to define alpha we are putting a minus sign before that, and therefore, this alpha is always a positive quantity. What other expressions we have in Cp minus Cv? We have specific volume, volume has to be a positive, T is the absolute temperature, so that also has to be positive, alpha is also positive. Now, that leaves us with beta. Now, beta is positive or negative? Beta is volume expansivity, which gives the change in volume with temperature. Now, for generally for substances, as the temperature increases, volume also increases, and therefore, V and T goes in the same direction. So, beta is also a positive one. So, we can write beta is also a positive one, but is it true always? It is not true always. For most of the general situation, volume keeps on increasing with temperature, but just think about the anomalous expansion of water. Water, as the temperature keeps on decreasing, its density keeps on increasing, but till that 4 degree Celsius. Below 4 degree Celsius it goes in the opposite direction. Like if we plot specific volume with temperature, for most of the common substances with temperature specific volume keeps on increasing, but that does not happen for water. For water, as the temperature decreases, specific volume keeps on decreasing till 4 degree Celsius. At 4 degree Celsius it reaches a minima or density reaches a maxima, and if the temperature is reduced further, the volume keeps on increasing till the 0 degree Celsius or till the freezing point at that constant, at that corresponding pressure. That is why ice is having lesser density compared to water, and ice is able to float in water, because the volume of ice is higher, specific volume of ice is higher than liquid water, or density of ice is lower than liquid water. Now, if we think about, or if we divide this zone, if we divide this region into two parts, in this direction temperature and specific volume both are going in same direction, thus therefore beta is positive. But what about the left hand side? Here, as the temperature is decreasing, volume is increasing, so beta is negative. Such anomalous expansion, though very rare, but can be found in a few other substances as well, and therefore beta can be positive or can be negative. But all this discussion does not matter in this context of the Cp minus Cv expression, because here we are having a beta square. So, beta square is always a positive quantity, and therefore, the Cp minus Cv given by the Mayer relation is always a positive quantity, or we can write Cp minus Cv is always greater than 0 or maybe greater equal to 0 in some limiting case. Therefore, Cp is always greater equal to Cv, that is specific heat at constant pressure is always greater than the specific heat at constant volume for any substances. Now, how much greater it will be, that will depend upon the PVT relationship, but it can never be less than Cv. At the limiting case it can be equal to Cv. Second important conclusion, as the temperature keeps on decreasing, Cp minus Cv difference also keeps on decreasing, or magnitude of Cp minus Cv, and when absolute temperature becomes 0, then Cp is equal to Cv. That is the limiting case that we are mentioning. The Cp and Cv will be equal to each other when we reach the absolute 0 temperature, but in general, as the temperature keeps on reducing, the difference between both the specific heat also starts to diminish. And the third conclusion, when you are talking about a truly incompressible substance, truly incompressible substance means whose specific volume does not change, then what will be the expression for Cp minus Cv? Mayer relation, it is difficult to obtain from Mayer relation, but just look at this. Here, when we are talking about a truly incompressible substance, this particular differential is equal to 0, because specific volume is not changing, and therefore Cp minus Cv is also equal to 0. That means, for a truly incompressible substance, both the specific heats are identical to each other, and that is why when you talk about an incompressible substance, generally for solids or liquids, we do not need to bother about two specific heats, we can just stick with a single specific heat generally given by C. However, when you are talking about gases, they have much higher level of compressibility, and therefore, for gases we need to consider Cp and Cv separately. So, with the Mayer relation, now we know how to calculate the difference between the two specific heats for any given situation. I would like to close up on this particular lecture by discussing another example. Again, we have the ideal gas equation of state, but here we shall be talking about the expressions for specific heats Cp and Cv. There are two expressions we have developed. One is the Mayer relation, but before that we all developed another relation for Cp as a function of temperature and pressure. It was Cp naught for that given temperature minus integration of T dou 2V dou T2 at that P dP for the pressure P1 to P2. So, this was the relation that we already had, we have developed for Cp. Now, let us try to apply this for an ideal gas situation. For ideal gas, Pv equal to RT or V is equal to RT upon P. So, if we differentiate the specific volume with respect to temperature, maintaining pressure constant, then what it will be? It will be equal to R upon P. If you differentiate it once more to get the differential, this particular differential, we shall be having dou 2V dou T2 at P, then what we have? We are basically trying to evaluate dou T of this quantity R by P, maintaining pressure constant. R itself is always a constant, therefore, this is equal to 0. So, for this scenario, what we have is Cp naught T, that is for ideal gases, pressure has no role on the magnitude of specific heat, we can get it only from the information of temperature. Whatever absolute 0 pressure temp or ideal gas in specific heat it has, the same will continue for any pressure level, and therefore, when we are talking about an ideal gas or specific heat for an ideal gas, we do not need any information about pressure, temperature alone is sufficient. So, here we get Cp. Now, let us try to evaluate the relationship between Cp and Cv, that is a Mayer equation. For this, first we evaluate beta. So, beta is 1 by V dou V dou T at constant pressure. So, let us evaluate this 1 by V. Now, from the ideal gas relation, dou V dou T at constant pressure we already have. So, from there we have R by P, that is R by P into V, and if we write R by dou V dou T at constant pressure is coming as R by P into V, and if we put the expression again, P V is equal to R T. So, if we put it, this is coming 1 by T, that is for an ideal gas this volume expansivity is inversely proportional to temperature, and that also gives you the dimension of this dimension of this beta. What it will be? It is reciprocal to temperature. So, its dimension is inverse of temperature, or in SI unit it will be Kelvin inverse. Now, look at alpha. Alpha is equal to minus 1 upon V dou V dou P at constant temperature. So, we have Pv equal to RT, that is P is equal to RT upon V, or I should have written in the other way, V is equal to RT upon P. So, dou V dou P at constant temperature, we are differentiating with respect to pressure. So, what it will be? We have RT into P to the power minus 1, that is we have minus RT upon P square. So, if we put it back here, minus 1 upon V to RT upon P square and minus of that. So, we have RT upon P square into V and RT itself being P into V, this becomes 1 upon P. So, what is the unit of this isothermal compressibility? That is the reciprocal of pressure, like in SI unit it can be Pascal inverse or kilopascal inverse or megapascal inverse, whatever we would like to represent. So, for an ideal gas, isothermal compressibility is just the reciprocal of pressure and volumetric expansivity is reciprocal of temperature. Now, we use the Mayer equation where we have Cp minus Cv is equal to V T beta square by alpha. So, we are putting the expressions for alpha and beta here. We have V T beta square, beta is 1 upon T. So, we have T square in the denominator and alpha is 1 upon P. So, P goes in the numerator. So, we have PV upon T using PV equal to RT upon T becomes equal to R. That is for an ideal gas, the difference between Cp and Cv is a constant which is given as the gas constant itself. I just wrote this equation just a few slides back, this is the proof for this. For an ideal gas, we can calculate the difference between Cp and Cv using Mayer equation to get the gas constant itself. For any real gas, we need to use the corresponding equation of state. I would like to request you to perform the same exercise for the van der Waal equation of state. That is when you have P plus A upon V square into V minus B equal to RT as your equation of state or the pivot relationship, then calculate the expression for Cp and also the difference between Cp and Cv for this van der Waal equation of state. That will be your exercise for this particular lecture. So, I would like to complete here for today's work, where we have actually I had these expressions here. So, today we have developed the generalized relationship for ds, then we have done several exercises about how to use the generalized expressions for du, dh and ds, then we have developed the generalized relations for specific heats and finally, the Mayer relation which gives the difference between Cp and Cv. So, that is it for today. In the next lecture, we shall be discussing about two unrelated topics which are the Joule-Thomson coefficient and also the enthalpy calculation for phase change processes. Till then, you review this particular lecture, and as I have asked you to develop the relationship between Cp and Cv for a van der Waal gas or van der Waal equation of state, please try that, so that once we start the next lecture, you will be in a better position to handle any other kind of problems. So, thank for your attention, take care.